Math Singer, yum!
Perhaps the most obvious way to evaluate the integral of x cubed over the square root of 4 plus x squared is by applying a method that is often referred to as trigonometric substitution. In this example, the denominator of the function x cubed over the square root of 4 plus x squared contains an expression of the form constant plus variable squared. Integrals that involve expressions of the form constant plus or minus variable squared, or variable squared plus or minus a constant, can often be evaluated by applying a trigonometric substitution that is suggested by one of the Pythagorean identities. Now, if you're like me, the only Pythagorean identity that you can probably remember with confidence is that sine squared theta plus cosine squared theta is equal to 1. The other Pythagorean identities follow easily from this one by dividing both sides by either sine squared theta or cosine squared theta. In this case, we'll divide both sides of the Pythagorean identity by cosine squared theta to reveal that tangent squared theta plus 1 is equal to secant squared theta. Observe that tangent squared theta plus 1 is also an expression of the form constant plus variable squared. In the case of this identity, the constant is equal to 1. However, the constant in our integrand is a 4. If the x squared in our integrand were equal to 4 tan squared theta, then we could factor 4 out of both terms under the radical and be left with 4 times the quantity tan squared theta plus 1. This seems like a reasonable plan, so we will proceed by wishing that x squared were instead equal to 4 tan squared theta. This is our creative step. We could have chosen to wish for any substitution that we liked in order to change the appearance of our integrand. Everything we do from this point forward is merely a consequence of allowing our wish to be granted. Our first consequence is to notice that x is equal to 2 tan theta. From there, dx is equal to 2 secant squared theta d theta. Incorporating our wish and these two consequences into our integral yields quantity 2 tan theta cubed divided by the square root of 4 plus 4 tan squared theta times 2 secant squared theta d theta. Well, 2 tan theta quantity cubed is equal to 8 tan cubed theta. And factoring 4 out of both terms in the denominator and then bringing the 4 outside the radical as a 2 yields 2 times the square root of 1 plus tan squared theta. All of this is being multiplied by 2 secant squared theta d theta. From here, the 2's in the numerator and denominator go away together as a 1, and we can bring the factor of 8 outside the integral. This leaves us with a numerator of tan cubed theta secant squared theta. And the 1 plus tan squared theta in the denominator can be written as secant squared theta, which was the reason for choosing the substitution that we made in the first place. Finally, since the square root of the square of secant theta is just secant theta, we can divide the secant squared theta in our numerator by the secant theta in our denominator and write our new integral as 8 times the integral of tan cubed theta secant theta d theta. We have now successfully written our original integral in terms of x as a brand new integral in terms of theta. It is now our task to see if we can find a way to evaluate our new integral. In order to evaluate 8 times the integral tan cubed theta secant theta d theta, we can begin by writing tan cubed theta as tan squared theta times tan theta. Why would we do this? Well, recalling that 1 plus tan squared theta is equal to secant squared theta, it follows that tan squared theta is equal to secant squared theta minus 1. Therefore, we could replace tan squared theta with secant squared theta minus 1. This gives us a very simple integral in disguise. By letting u equal to secant theta, we see that du is equal to tan theta secant theta. Therefore, our new integral can be written as 8 times the integral of u squared minus 1 du. Of course, this is equal to 8 times the quantity of 1/3 u cubed minus u plus c. Substituting secant theta back in for u gives us that 8 times the integral tan cubed theta secant theta d theta is equal to 8 times the quantity 1/3 secant cubed theta minus secant theta plus c. Incorporating this result with our earlier work, we now see that we need to find a way to express this answer in terms of x. That is, we need to express our final answer in terms of the variable in which the original question was asked. To do this, let's return to the line that provides the relationship between x and theta. Since x equals 2 tan theta, it follows that x over 2 is equal to tangent theta. Therefore, theta must be equal to the arctangent of x over 2. This means that if we have a right triangle that contains this angle theta, then the tangent of theta must be equal to x over 2. This is because the tangent of the arctangent of x over 2 is just x over 2, since the tangent and arctangent functions are inverses of each other. Well, if the tangent of theta is x over 2, then the opposite side of theta, divided by the adjacent side, must be equal to x over 2. The simplest way to label the side lengths of our triangle so that this is the case is to label the opposite side as x and the adjacent side as 2. It follows from the Pythagorean theorem that the square of the length of the hypotenuse must be 4 plus x squared. In other words, the length of the hypotenuse is the square root of 4 plus x squared. From this, we can see that secant theta, the hypotenuse over the adjacent side, must be the square root of 4 plus x squared all over 2. Substituting this expression in place of secant theta and multiplying through by 8 gives 8/3 times square root 4 plus x squared over 2 quantity cubed minus 8 times square root of 4 plus x squared over 2 plus c. This reduces to 1/3 times the quantity 4 plus x squared to the 3/2 minus 4 times the quantity 4 plus x squared to the 1/2 plus c. We could leave our final answer in this form, or we could choose to go a bit further by factoring out 1/3 times the quantity 4 plus x squared to the 1/2 from both terms. Doing so leaves 4 plus x squared quantity to the 2/2, that is, 4 plus x squared, from the first term, and 4 divided by 1/3, which is equal to 12, from the second term. Therefore, our final answer is 1/3 times the quantity 4 plus x squared to the 1/2 times the quantity x squared minus 8 plus c.